trick to doing that, you didn't have to write that part out because this 10 drops, 10 over 5 becomes 2, and 10 over 2 becomes 5. Now you've got x plus 1 quantity squared minus 24 is 75. Okay. From there, it's a relatively simple problem. Morning, sir. Okay. As you put that stuff through, you add the 24. Square root it, plus minus, and you're going to get x equals -1 plus or minus 3 root 11. Because 99, you can take out the 9, 9 and 11, square root 33. And that's your answer. You don't have to write anything else. The trick, anytime you've got a fraction like that, guys, multiply it out by a common denominator, and it goes away. Very simple setup to do it that way. Okay? Does that help? What was the other one you were looking at? Which one? 24 on the other one? Sure. Do. Such a pretty song. Of course, you pick the ones with all the S's in it. Are you guys changing everything to X's as you're writing them out? No. You can. It's okay. I would, because that way it's easier to read. So 3x squared minus 1 is 7x squared. Okay? Take out the little guy. -1 equals 4x squared divided by 4. And you get -1/4 is x squared. Square root. When you square root a fraction, you're square rooting the numerator as well as the denominator. A lot of times people, and if you're one of those types of persons that likes to write slashy fractions, slap your hand right now and say, I will never do that again. Slashy fractions are evil. What? Slashy fractions are evil. No, they're not. You cannot do other math later on with slashy fractions. Get rid of slashy fractions. Slashy fractions should never been shown. You corrupted your brain the minute you saw slashy fractions. Please, if you write slashy fractions, slap yourself in the wrist and say, don't ever do slashy fractions again. Not pat yourself in the back with slashy fractions. This is a penance. You're in trouble. Yeah, no more slashy fractions. Slashy fractions? No slashy fractions. Anyway, so you get the square root of -1 over the square root of 4, plus or minus, is x. What's the square root of -1? And what's the square root of 4? 2. So you get plus or minus I over 2. A lot of times when you do slashy fractions, you will forget that you have to square root the denominator. So no more slashy fractions. What else we got, guys? You used your imagination, okay? I'm sorry. Yeah, it's lovely pictures. Hey, did you guys know you could graph these too? Yeah, I'm doing it right now. No, there's actually a plot way of doing it. You just call one the imaginary plane, the other one the real plane. It's imaginary and real. It's quite literally, you call the y-axis imaginary, your x-axis the real. So if it's 3 plus 4i, you go over 3, you go up 4. It's kind of like normal, but we don't have to do this. I'm not going to do this. Same thing with the absolute value stuff. I'll save the absolute value of imaginary numbers for you guys for pre-calc. I gotta let them teach you something. Because they do have absolute value. Because there's a distance from 0. It's exciting. What else? Anything good? No. All right, save this. We're going to add more to it today. What I wanted to do today was kind of re-emphasize the whole I just wanted to reiterate this with you guys because you didn't your brains yesterday seemed like they were well, yeah, they're full of holes, they were Swiss cheese. It was you were having a hard time imagining what was going on. So what happens here, remember, anything to the first power is always itself. So I to the first power is still just going to be plain old boring I. Okay. I squared, on the other hand, you have to remember that I is represented by this. Oops. All these dots. I is represented as the square root of -1. Now, when you square when you square a square root, it just gets rid of it undoes the root. Okay, so I've said this before, the square root of junk squared is always junk. So when I take the square root of -1 and I square it, I get -1. Okay. Now, I want you to think of, again, why this works. As you're working with exponents, as you're raising exponents, that just means if x cubed is x times x times x, or x squared times x to the first, you can break them apart because when you're multiplying, all you're doing is adding your exponents together. So that means that once you know what I squared is, -1, you can replace it. So if I squared is -1, I can say that that's the same thing as saying I squared times I to the first, which is -1 times the square root of -1, which is -1 times I, or -I. That's why that happens. And then as you go to the fourth, it's just a matter of it's squared times squared. What was I squared? And then the pattern repeats. I, -1, -I, 1. I, -1, -I, 1. That's all it is, as it rotates through. So if you want to figure out what I to the 73rd power is, all you have to do is figure out how many times does 4 go into 73, and then whatever the remainder is, tells you which one it lands on. And it works every time. So if you had to figure out I to the 73rd power, how many times does 4 go into 73? 18 times. One. Yeah, 18 times, and then there's how many left over? 1. So this is basically I to the 4th 18 times, which is equal to 1. And then it's I to the 1st. What's I to the 1st? I. So this would equal I. That's all you got to do. That's how that works. The pattern itself repeats itself over and over and over. Right. You don't have to write it out 18 times out of the 4th to know that when you multiply all those together, you're going to get 1. Just remember that if you divide out by 4, whatever the remainder is, tells you which one it falls on. Right. I just wanted to reiterate that yesterday, because I know yesterday you guys were kind of going, right. It was a lot of that. Yeah, you know, I'm pretty good at sensing a crowd. I know how to feel a room, and when I saw that, what's that? Why? You can take an imaginary walk. Well, let's do something different with imaginary today. So, what I want to do today is something like this. It's a continuation of 5-4. There's nothing left in 5-3. We did all of 5-3. What I'm looking at today is just finishing up 5-4. What I'll probably do today is that I kind of cut and pasted a bunch of worksheet problems that I had lying around of 5-3 and 5-4, 5-2 of factoring, and some 5-1 setup graph stuff. That way we can start with the 5-3, 5-4 stuff today and then build it back into a bunch of review junk tomorrow for the quiz come Friday. What happens here in complex numbers is that complex numbers have a specific way of being written. Complex numbers are always written with an A, I think it's A plus BI, where A, this value of A is a real number, and this B is the coefficient of the imaginary, okay? It's coefficient of the imaginary number. It's just proper etiquette to put real numbers first before you put imaginary numbers. And I think you guys saw that when we were writing down our answers. That's kind of how we set this stuff up. So when you see things written, a lot of times what they do is that you will see them grouped as 3 plus 4i is a complex number. 2 minus 12i is a complex number. That's why it's represented within parentheses. That's just a grouping way to show it. Okay? It's nothing too crazy. It's just one of the rules. So what happens here today is that we're going to talk about how do we add, subtract, multiply, and divide complex numbers. Well, adding and subtracting is fairly simple. This is nothing more than combined like terms. This is nothing more than a combined like terms because you can treat I, coefficients with the I value, treat it like it's a variable. Okay? When I have these complex numbers written out with parentheses, I'm just adding. You don't worry about the parentheses. So basically this works out being 3 plus 2, which is 5. What's 4 minus 12? And there's your answer. Adding is really, 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 really easy. Okay? You're just combining like terms. Subtraction, on the other hand, since they group these things within parentheses, you have to be careful to distribute. That's the only trick. Right? That's the only trick. For example, if I'm looking at this, right? Complex number 7 minus 5i minus the complex number 1 minus 5i. What I have to do here is I can't just combine my like terms. Here, since there is a subtraction symbol in front of the parentheses, you have to distribute it to both pieces. That's the trick. That's the only trick you have to worry about, here and here. 7 minus 5i minus 1 plus 5i. What's your answer? 6. Combine like terms. Again, the only thing you have to worry about is that you have to distribute that negative. Once you do that, super fast. Adding and subtracting these things are really easy, but the only thing you have to worry about is when you have that subtraction symbol, you have to remember to distribute. And that's a common thing that most students, in AP calculus, when they have distributed property with negative, a lot of times the common mistake is they forget to set the secondary term. Happens all the time. Just remember you see that. Remind yourself to draw the arrows so it forces you to remember what to do. Okay? All right. Try that one. I'm sorry. Come on, sleepyhead, you can sit up and try. Come on now. See, yes, you can. I know. Here, shake his desk, mate. See, you can do that too. I can't. Come on, you can do it. All right. Oops. Distribute here, so we have 6 plus 2 minus 9i plus negative 8 plus 4i. When you combine these things, you always put the real numbers first. So 8 minus 8 is 0. Negative 9 plus 4 is negative 5. So your answer here is just going to be negative 5i. When you have a 0 for the real number, you don't have to put it there. If you do, are you wrong? No. Doesn't matter. You just write it as minus 5i or negative 5i. Again, it's a lot of combined like terms. Watch the signs as you distribute the negatives. That's really about it. What gets weird is when we have to multiply and do stuff. When we have to multiply and worry about things, that's where you're going to get an extra step. And you'll see where I'm getting at here real fast. So if I have 5i times the quantity negative 2 plus I need to remember, again, distribute. Okay. So 5i times negative 2 is negative 10i. What's 5i times I? 5i squared. Good. Now here's the thing. What's I squared equal to? Negative 1. Yeah. So this is where it happens here. You get, when you have an I squared, you have to remember that it's 5 times negative 1, which means my answer would be negative 5 minus 10i. Because when I simplify that, it's got to go in front. Okay? Because the rule is real numbers first. Okay? Yes, ma'am. It should be written real number first because that's the proper form. But I'm always going to write my real number first because that's the proper form. So that if we practice doing it, you won't forget it. Fair enough? Because you're right. What's negative 5 plus 3? Negative 2. And 3 plus negative 5 is still negative 2. It's still giving you the same complex number. It's just proper form. Okay? Does anything change when you have binomials? No. You just have to FOIL and then combine like terms. You would FOIL and combine like terms. Excuse me. Number first, outside, inside, last. First, outside, inside, last. Negative 8i squared is equal to what? 8. Very good. Because you get negative 8 times negative 1. So it becomes a positive 8 at the end. So you get negative 7 plus 18i minus 8 times negative 1. And that's where this becomes a positive 8. That's one of those things you just got to remember. Anytime you have an I squared, you're going to automatically rewrite it as negative 1. So your final answer would just be 1 plus 18i. Not terrible? Here's where it gets weird. Did I write no? You know what? I don't know. I don't know what to do now. How about I do that? And then let me know if it starts bothering your eyes. Oh, sorry. That was pretty funny. Anyway, just like when we had radicals within the denominator, it's not proper form to have them there. We had to rationalize. Remember that? Well, we kind of do the same thing with imaginaries. What we're going to do here is we're going to multiply by some form of the imaginary to get rid of the imaginary within the denominator. Now, what I want you guys to think of is how polynomials work. If I FOILed that out, what would I get? X squared minus 16. Very good. Remember what this was called? It's called a difference of squares. Okay? Remember, we called it difference of squares because the first term is a perfect square, and the last term is a perfect square, and the symbol in the middle was a subtraction. By doing, whenever you have a difference of squares, you have FOILed out terms that are plus minus of the same values. Okay? I wonder if you can go more than 30 seconds without looking at your phone. Do you think? All right, put it in your pocket. See if you can do it. In a pocket, or put it on my desk, and you can go the rest of the period without it. I know you can do it. Guys, I'm pretty lenient about the whole phone thing because I get it, but it's gonna bite you in the ass one of these days as you guys are going through your things. You're gonna miss something. You're not gonna know how to do something. So what we want to do is I want to create some form of a perfect square in the denominator. Because if I square an I value, what happens to it? It becomes -1. So if I create a difference of squares in a denominator, if I multiply it out, 1 plus 2i divided by 1 plus 2i, isn't that still a factor of 1? So am I changing the form at all? I'm just multiplying by a factor of 1. So what happens then, move this down so we go. What happens then, do this in 2 spots. If you FOIL out the denominator, you wind up with 1 minus 2i plus 2i minus 4i squared. You okay with that? FOIL it out. First, outside, inside, last. I might have done my insides first, but yes, sir.
How can we multiply this positive 2i?
Because if I had a negative 2i, I would still have an I in the denominator. What happens with the 2i and the negative 2i here? It cancels out. So what happens is this drops, and you get 1 minus 4 times -1, which is 1 plus 4. So your denominator becomes 5. That's why I multiply by what's called its conjugate. Multiplying by conjugates is what we're doing here. You're taking whatever that binomial term is, you're multiplying it by itself with a different sign. That creates a difference of squares. That eliminates for the I value here, it eliminates the value of I. If this was a square root, if it was 1 plus the square root of 3, I would multiply top and bottom by 1 minus the square root of 3. Because it's a difference of squares, the value of the root would go away. It's the same basic principle as you guys have done with square roots in the past, but here you're just dealing with an I value instead. Okay? So you take care of that with the denominator, it goes away. I still have to FOIL out my numerator, and it's okay to have i's in the numerator. So if you FOIL out the numerator, you're going to get what? 5 plus 10i plus 3i plus 6i squared. Positive 6i squared turns into a what? Negative 6, very good. So then you wind up with negative 6 plus 5, which is negative 1. 10i and 3i is 13i. So you get negative 1 plus 13i. And that's how that simplifies. Okay. It looks really, really weird, but in essence, all we're doing here is we're kind of doing the same thing that you've done in the past. If it was 2 over 1 plus the square root of 5. When you had to simplify that before, you'd multiply the top and the bottom by 1 minus the square root of 5. If you FOIL that out, you get 1 minus root 5 plus root 5, it drops. Then minus root 5 quantity squared. And then it drops itself out. The square root goes away. It's the same principle, but now it's just I. You're creating a difference of squares in the denominator to get rid of I. Okay. Try another one. And I might as well throw it with the roots too, just to have a little bit of fun. I have the square root of 10 divided by the square root of 10 minus I. Why don't the root 10s cancel out here? Do you guys remember? No, that's not the reason why. But why can't I just cross off the root 10s and say it's 1 over negative I? Because it's a binomial in the denominator, because there's subtractions. You can't simplify over subtraction. You can't simplify over addition. You can only simplify when you have monomial. Anything. And numbers in general. Yeah. So here, what's your conjugate going to be? What are you going to multiply top and bottom by? Root 10 plus I. Okay. So you get top and bottom will be root 10 plus I. Okay. So if I FOIL it out and pick a little bit of space here. If I FOIL it out, what's root 10 times root 10? 10. I have I root 10 minus I root 10. Just to show us all the steps for right now. And then I have minus I squared. The I root 10s drop. Everybody okay with that? And then what's negative I squared? 1. Very good. This equals a positive 1. Because I squared is negative 1, so minus negative 1 is plus 1. So your denominator becomes 11. Your numerator, distribute that root 10 in, you get root 10 times root 10, which is 10. And then it's plus I root 10. So your answer would be 10 plus I. And that's how it simplifies itself. Yeah. Yep. we're simplifying that out, that's exactly what your answer would be. Let's see. I think I got one on here that you might figure out a pattern that happens. I want to change this a little bit. Or not. I'm changing that from 3 minus 4i over, I'm going to do it as 3 minus 4i over 1 plus 2i. I like to show it with a number in front of the I value. You might see the pattern a little bit quicker. Excuse me. A lot of times when we have these weird complex fractions, but it's not a complex fraction, excuse me. Just these fractions like this, and there's a lot going on that you can do with the numerator and the denominator. I like to just take them one at a time. Take care of the denominator all the way through, and then go back and do the whole numerator. What do you guys multiply top and bottom by? 1 minus 2i. Good, that's the conjugate. So if you multiply top and bottom by 1 minus 2i, as you distribute and FOIL out your denominator, you get 1 minus 2i plus 2i minus 4i squared. Middle terms go where? Multiply by. Middle terms go bye-bye. And what's negative 4i squared? 4. So what's 1 plus 4? Have you figured out the pattern yet? What's that? I'm talking, there's a pattern for the denominator. Not necessarily. What is it, Bella? What is it? Oh, okay. What's 1 squared? Wait, go on. What's 1 squared? What's 2 squared? What's 1 plus 4? What's the square root of 10 squared? What's the coefficient here? What's 1 squared? What's 10 plus 1? What's 1 squared? What's 2 squared? What's 1 plus 4? Plus the second 1 squared. Yeah. There's a shortcut pattern that happens so that you don't have to FOIL out the denominator all the time. It's always going to be first term squared plus the coefficient squared added together. It will always work like that, no matter what it is. The numerator, though, you still have to FOIL out and simplify. But the denominator, it's a shortcut pattern. Okay, there's that nice little shortcut pattern to it. Okay, so here, numerator again. Here I still have to FOIL it out. I get 3 minus 6i minus 4i, 3 minus 6i minus 4i plus 8i squared. It's going to be a negative 10. Are we okay with that? Negative 10i. And then obviously the 8i squared becomes 3 minus 8 is. So we wind up with what? Negative 5 minus 10i. Ooh! What can I do now? No. Everything everything is divisible by 5. There's a common factor. Okay. This, when you have, and that was the same idea, is that you can't do this because that's not mappable. Okay, that's unmappable. But since it's a singular term in the denominator, that means it's a common denominator for both pieces in the numerator, which allows you to do this. What's -5 divided by 5? -1. And what's -10 divided by 5? Okay. And it's just coincidence that it's the same values that you kind of start. It doesn't happen all the way like that. But every once in a while, you can simplify the terms when you have a singular term in the denominator. You can't just cross off the first parts. And this is common when you guys did quadratic formula in Algebra 1. Every once in a while, you were able to do that as well. You know, you were able to simplify your denominator to what parts were in front of the root and the b value, the opposite of b. It happens. So watch for it and make sure that you don't split them apart. I think every once in a while, a text. Let's say this was a 2. Every once in a while, you might see in a textbook, it could have done this, -5 halves minus 5i. They might do that, so if you check your answers on anything, if you see something weird like that, that just means they split apart the common denominator into the two pieces, the two separate fractions, and simplified one. You don't have to do that for me, I don't care. But if it is something where we had this to begin with, yes, simplify them both. Okay, does that make sense? Yeah. One more of those real quick before we. I know we're running out of time here. Oh no, it's only 20 minutes. Oh wait, that clock is wrong. Correct, that one's right. What's the denominator going to equal here? 53. It's 4 plus 49, so it's 53. Okay. Your denominator will be 53. Does that see how we can do that? Because we know it's going to be 2 minus 7i. Give me 4 plus 49 at the end after you simplify all it out. So it's a nice shortcut to be able to do. You still got to FOIL out the numerator, but you kind of cut your masking in half. Well, I would say in half, maybe like 45%, because you still got to add. Was that -14 minus, sorry, no, it's plus 49i minus 6i, and then plus 21i squared. So that's -14 minus 21 is -35. Did I get out of sequence? First, outside, -7 times -7i should be plus 49. That's okay. So I got -35 plus 43i all over 53. That looks lovely. Yay, math. Like I said, what I did was I took a bunch of these combined like terms and set up parts. I kind of just cut and pasted them together. There's not as many as I hope, but well, it's the idea of the practice on them. Once you do a couple of them, it's really kind of the same thing. The way that like I said, the way I piecemeal this thing together, it's the first 4 sections. It's the first 4 sections on there. There's some factoring, there's some drafting, and then on the back there's a bunch of solving the equations, and then at the bottom of one of them it says perform the given operation with a complex number. If I'm looking at the one side that has kind of a 3 sets of columns. I'll get it in a second. If you look on that side, the bottom ones are what we did today. Working up is what you did yesterday. So if I were you, I would start at the bottom here, just start putting some on paper, and then start checking through some of these things, and we'll start going through a whole bunch of them. Then we'll talk about factoring and all the tricks of the trade of graphing again tomorrow. I've got a couple extra little notes to remind us of how we graph and do things like that as well. Yeah, Bella? I would say, I'm not gonna say, I want you to try the ones on the very bottom there, because that's what you did today. But then we're working back upwards of solving more equations. You know, take a look at the ones with the fractions and the combined like terms, stuff like that. Yes, sir. Not all of it. No. Again, I'm starting some review junk here with you guys. I would ask that you I would ask you to get those imaginary combined like term ones done for tomorrow. If you've got time to start practicing the other equations, I would work upward. And then we'll worry about graphing and factoring again tomorrow. We'll talk about that with some more sheets that I have as well. Okay? Wanted to kind of start piecing it together for you guys.